Alright, hey guys, welcome back to ACE-IB. Today we're going to be talking more about statistics, specifically discrete probability distributions. So a few videos ago we talked about discrete and continuous variables. Now remember that a discrete variable means that the data can only take certain value. So this can be something like how many people are in a class, but it can't be something like the temperature of the room, because the temperature of the room can take realistically infinite values. So I also want to go over another definition, that is the random variable. So a random variable is, a random variable represents in number form the possible outcomes for a random experiment. So sometimes a random variable might not actually represent numbers necessarily, it can also represent choices. For example, maybe you were asking if students prefer chocolate ice cream or vanilla ice cream. They could also refer to the choices in that way. Now, a discrete random variable, you would basically put them together. It's a variable quantity which occurs randomly in a given experiment, which can only assume certain values, usually integral values, like the example where we were counting students. And a discrete probability distribution gives the probability associated with each value of a discrete random variable. So now, let's say that x is a discrete random variable, which I will just write as DRV, discrete random variable. With each of the possible outcomes xi, so x can have a few outcomes. Let's say they can either be x1, x2, x3. Let's just say there's only 3 outcomes for now. Basically, there could be 3 choices or 3 outcomes when we take this data. Then we associate a number, so let's say px equals xi equals pxi. And that is called the probability of xi. Basically, it's the probability that xi will occur. I should know that this is big P and this is small p. So the numbers pxi must satisfy the following conditions. First of all, p represents a probability. So for all of the xi's, pxi must be greater than or equal to 0 for it to actually be a value. And the sum of all the pxi's from I equals 1 to n must be exactly 1, meaning that all possible choices or outcomes of the random variable x has been considered. So sometimes you're going to see a question asking to show that some sort of function is a probability distribution function. What you basically have to show is that the function satisfies this. Alright, so now let's look at an example problem. Show that px equals x squared plus 1 over 34 for x equals 1, 2, 3, 4 is a probability distribution function. Remember, to show that this is indeed a probability distribution function, we just need to show 2 things. First of all, px for all xi must be greater than or equal to 0 for any I, and the sum of all pi's must be 1 for I equals 1 to n. Now, what we can do here is we can make what's called a probability table. What we do is we put the variable x on the top row and the value of px on the bottom row. So, according to the probability distribution function that's given here, if x equals 1, then px would be 1 squared plus 1, which is 2, over 34, 2 over 34. Now, I'm not simplifying this because it'll be much easier to see the sum after we write out all of these. Similarly, for 2, this would be 2 squared plus 1 over 34, which is 5 over 34. For 3, that would be 10 over 34. And for 4, that would be 17 over 34. And we can test that this is a probability distribution function, first of all, by seeing that all the px's are indeed greater than 0, or equal to 0, and so we put a check mark beside that. Then we check that the sum is equal to 1. We can add all of them together. And we see that indeed 2 plus 5, that's 7, 17, 17 and 17, 34, which is 1. So we know that the second statement is true as well. So therefore, px is a probability distribution function. Alright, so now let's go ahead and talk about the mean and expected value of a discrete probability distribution. The mean, also known as the expected value, is represented by mu, or the expected value ex, and that's going to be equal to the sigma of I equals 1 to n xi times p xi. So the way you think about this is that for all of the different choices, it is the value of that choice and the probability of that choice. So what this basically does is that it puts a weight on each of the possible outcomes. And depending on that weight, when you calculate the probability times the actual outcome, it'll give you the mean or the expected value. Now, the variance of a discrete random variable is noted as follows: sigma squared, so that's variance, or Vx is equal to the expected value of x minus mu squared. Remember, that is just the definition of variance, which is equal to sigma. So now we're just writing the expected value using sigma notation. Sigma I equals 1 to n xi minus mu squared times p xi. And then we can go one step farther and actually separate this into sigma I equals 1 to n xi squared minus 2xi mu plus mu squared times p xi. So all we've done here is that we've added we've separated and expanded the squared term. And we can simplify this one step further to find that this is just x squared times pxi. So in other words, this is sigma I equals 1 to n xi squared times pxi minus this term, which is sigma I equals 1 to n 2 xi mu times pxi plus mu squared, because the sum of all the pxi's is just 1. Oh, sorry, forgot about the squared here. Okay, so what can we do here? Right, well, we notice that xi squared times pxi, that is just the expected value of x squared, right? It's exactly the same as ex, except xi is squared. So that's just the expected value of ex squared. Then we take a look here. xi times pxi, well, that's just mu, right? From here, especially when you put it into the sigma, when you sum it, that's just going to be mu. So this is actually 2 mu times mu, which is 2 mu squared. So minus 2 mu squared plus mu squared essentially turns into minus mu squared. Or if we want to rewrite this, this would be ex squared minus ex all squared. So for a discrete random variable x, the variance of x is defined as sigma squared, or vx, which is ex squared minus e to the ex all squared. Okay, so now we're going to talk about a special type of discrete probability distribution, which is the binomial distribution. This is a special type of discrete probability in that there are only 2 choices. You can either choose true or you can choose false. Well, this is an example. Or maybe you can either choose yes or no. Or you can only choose to vote for one person or the other person. With this, since there are only 2 choices, there can only really ever be 2 of the outcomes. And therefore, we can simplify our equations quite a bit. Specifically, if the probability of x being equal to x, which is basically the probability saying if we were to ask x amount of people if they would answer true or false to this question, and we want we want small x amount people to answer. This will make a bit more sense when I give an example, but basically the probability of a binomial distribution is as follows. N choose x times p to the x times 1 minus p in minus x. Now, there are some assumptions that we make here. The first assumption is that every time we run this probability distribution for a binomial distribution, there's always a certain chance p that we will get true, and a certain chance that we will get false. Now, since there's only 2 choices, the other chance would simply be 1 minus p. Then, if we want to see, let's say, how many people would say yes or true to our question, if we ask big X number of people, then the probability would be this. Basically, it's the binomial distribution, right? The formula for the binomial distribution. It is p to the x, how many times we will choose p, or how many times they will answer true, which is we want x times, and how many times they will answer false, which is going to be n minus x times. Then we basically do a permutation of the different orders that we can get trues and false in, which is going to be n choose x. So this is the probability distribution for a binomial distribution. Now, in terms of the expected value and variance, these are much easier. So the expected value for a binomial distribution is simply n times p. And the variance for a binomial distribution is just np times 1 minus p. So a binomial distribution, just to sum it up, is useful when there are only 2 possible choices. And we usually give each choice a certain probability. Now, if one is p, then the other one has to be 1 minus p. And we can represent the probability that when we ask big X amount of people, that we will get small x amount of truths as this. So all three formulas are on your formula sheet, so you don't have to memorize these. Alright, so that's it for this video. In the next video, we will be doing some practice problems on discrete probability distributions, on some distributions with more than two choices, as well as the binomial distribution. Thanks for watching, and if you like our videos, please leave a like and subscribe. It helps the channel grow, and so that we can reach more viewers. That's it for today's video. I'll see you in the next one. Goodbye.